In this very building, and thank you for joining us, Ricardo. We will hear a presentation, in fact, a kind of a continuation of the presentation of last week, but today about the Bernstein-Landau paradox in fusion plasmas. So please, Ricardo.
So thank you. Well, thanks to the organizer for the invitation, and again, congratulations, Vilker, for your birthday. So yeah, this is a problem in plasma physics, and it's based, this talk, in a paper in Journal of Statistical Physics with Frédéric Charles, Bruno Després. They are from Laboratoire Lyons at Sorbonne Université. And well, Alexandre Rege at the time was a graduate student. Now he's in the ETH, the Federal Polytechnic Institute in Zurich. And well, I will talk about, well, a problem in plasmas, having in mind fusion plasmas, but no, not only fusion plasmas. Now, and then we have the Blasov-Poisson system for the plasma. And the origin is the following. We approximate Newton's equations for a very large number of charged particles that are moving in an electromagnetic field, right? So there is going to be the induced electromagnetic fields by the dynamics of the plasmas and a constant external magnetic field. And then this is described by there are so many particles that you have to use a continuous approach. And then we say there is a density function, very much like in the gravitational case, for those of you who listen to that talk, f, t, x, and v, t, time, space, velocity, that gives, well, the number of particles, or the distribution of particles time t in the position x with velocity v, okay? And x then is the position, and we are going to take the following situation. The movement is one-dimensional along x. However, the velocity is two-dimensional. This is because we have a magnetic field. And the idea is that, well, of course, each individual electron is having a complex movement, but on the end, there is a kind of a compensation, and we move along one direction in spite of the fact that there are two-dimensional velocities. This is so-called 1.5-dimensional problem, and it's a model which is very much used in plasma, in problems in plasma. So this is to simplify. So the velocity v is v1, v2, and x corresponds to v1. And this is solution to the Blasov equation, and as I already mentioned, it was discovered, this is from the 30s, but it was discovered by Jeans in the gravitational case some 20 years earlier. What it means, yes? Well, I mean, there is V1 is in the direction of the average motion, and V2 is the perpendicular to the direction of the average motion. So we are thinking that there is a compensation, and then eventually the result is that the distribution function depends only on one coordinate, right? It's a model, but it's a common model. You could think paradoxical that, the density depends only one coordinate, in spite of the fact that the velocities are two-dimensional. But this is an average, right, for the system. Okay. And what means the Blasov equation is that if you follow trajectories, the mass is conserved. But it can be derived as a limit of a large, very large number of particles. This can be found in textbooks. So now we are going to assume that the motion is periodic, 2p periodic, so x belongs actually to 0 to pi with periodic boundary conditions. And this is, again, one configuration that somehow corresponds to a tokamak, but you're having a confined situation. In the galaxy dynamics, you are in whole space, but here as well, you could consider the whole space, right? And then there is the electromagnetic Lorentz force, which is given, well, this is the electric field, the magnetic field, and I will make the assumption that the magnetic field is constant and perpendicular to the V1, V2 plane. Now, constant, what do I mean? The total magnetic field is not constant because there is a small induced magnetic field, but here I should have the induced magnetic field plus the large constant external magnetic field. Think again in a tokamak, and I just take away the small induced magnetic field. Then I will only have an electric field here, induced, right? And then it's along the third direction. So we are in a plane and electric field perpendicular. The motion is along one line on the average, but there is really motion in the plane, right? And the electric field is directed along x1, which actually is going to be x now, which is the motion of the particles. So then we are going to think the following. Those are electrons, light electrons that move. So the charge of the electrons is -1, the mass is 1, and then there's going to be ions as well. Now the ions are heavy, so we think they do not move, they are fixed, and the electrons are truly the dynamical particles here. So, and then, and then we have the Gauss law, and well, it might be peculiar, but I take the charge of the ions equal, or maybe the density of the ions equal to 2 pi. This simplifies considerably some formulas later, but it's just a convention. So this now is the Gauss law, divergence of the electric field equal to the density of charge, the charge of the ions, minus the charge induced by the distribution. So it's the integral velocity of the distribution function. Good. And this one then is the charge density of the particles, the electrons say, right? So this is the setup. And then the Blasov-Poisson system is the following, the Blasov equation, and well, this actually is still the Gauss law, but I introduce a potential, and then this is Poisson's equation. Now, the true system will be Blasov-Maxwell, but this is an approximation where you only keep the Gauss law out of all Maxwell's equation, you only keep that one. We are going to recuperate the Ampere equation later on. And this is a fundamental system not only here, in particular in problems in plasmas, right? And then again, the potential is periodic. So the question that we wish to address is the following. Well, what is the long-time behavior of the electric field. Now, suppose there is no magnetic field, and then there is the famous and important phenomenon of Landau damping. This is a picture of Landau in 1946, that he found that the lim T infinity of the electric field is 0. He considers, well, a linearized problem is everything is constant coefficient, so he did a computation using Laplace transform, and he found that. Now, we are in a system where energy is conserved. There is no dissipation, so just take basically any, well, there are conditions for this that for this I will not mention. Suppose that you have some electric field and eventually dies out. So this came as a surprise, and it disappears in many areas of plasma physics. It's a well-known phenomenon and very famous now, also even among mathematicians, right? So this is then the problem. And then, well, this is a remarkable fundamental fact. So it means the following, that all the energy of the field eventually is transmitted to the electrons, to kinetic energy of the electrons. A priori, there's no reason why, right? And, well, it has been studied a lot, and it's been studied. And there is a breakthrough by Cédric Villani and Mouot in these papers in Acta Mathematica 2011, that they prove that this actually remains in the nonlinear case. Even among the physicists, this was not so clear. And it's, well, one of the reasons, if not the reason, why Villani was awarded the Fields Medal. So then this made this problem famous among mathematicians, of course, right? So, and then there is currently a lot of work about mathematicians, physicists, and numerical analysts. So the numerical part is important here because there are, as I will mention, important applications of these problems, right? And from the physical point of view, there is the ITER project. If you're interested, they have a beautiful web page, which is a large tokamak that is being built in the south of France. And this is supposed to be of large enough scale in order that, well, eventually could lead, it would still be a research facility, but if successful, it will eventually open the way to production of electricity by fusion, and maybe contribute to solving the, well, global warming and so on. And also it's interesting, it's a global research undertaking involving the European Union, the United States, Russia, China, India, and South Korea. And in the uncertain and difficult times in which we live, is one of the few, well, it's a very nice, large-scale global scientific collaboration that still exists in spite of all the geopolitical issues that we all know about, right? So it's maybe the most important scientific project currently. So they have beautiful pictures of the magnets there, so if you like, you can take a look there. So now, however, then what happens when the magnetic field is different from 0? Well, just to remind you, in this case, we have the Blasov equation with the magnetic field. This term is absent if the magnetic field is not present. WC is V sub 0, which is the absolute value of the magnetic field. Well, and then we take again a potential, and we take periodic, we take the mean of the electric field equal to 0. If the potential is periodic, this has to be, right? Well, then there is the discovery of Bernstein. And what is the Bernstein-Landau paradox? Well, Landau damping disappears completely. And instead, under some conditions, Landau damping is even exponential in time, just goes away. And then the solution has oscillation and some recurrence that eventually we will explain the recurrence as well. So, and this came as a surprise, and it's called often the Bernstein-Landau paradox, and it is this paper, these two, those two, people, Sokubo and Stube, who coined the terminology Bernstein-Landau paradox, is to those people. So the aim of the talk is, to try to understand this as a problem in singular perturbation in operator theory, self-adjoint operators. And this will give an explanation, a rather simple explanation to this paradox, and also a numerical method. And I hope I will show you numerical results in the solution of this equation. It is three-dimensional, so it requires some care. So this is the plan of the talk. And so then the idea is the following. We linearize the equation around a homogeneous Maxwellian, as the physicists do. So we take this, and we expand in this form. Now, why I take this product here? Well, the natural norm for F is the L1 norm, because it's the total mass. And I wish to use Hilbert space. Then I need the scalar product. And then if we see, okay, if this is L2 and this is L2, then the product is L1. So it's more convenient to look to this from an operator theory point of view to do this, right? And then, I also expand the electric field, and the constant part I will take to 0. I wish the mean of the electric field to be 0, right? So, and then keeping only the linear terms, one get the linearized, magnetized Vlasov-Poisson system, which is this system, right? Vlasov equation, the Gauss law, mean equal to 0, and again here, the Poisson equation. So then what we get is the following. Okay, Vlasov-Poisson is the standard method. This is extensively used, right? And to analyze the dynamics of a very large number of charged particles moving in the presence of a constant external magnetic field, and also of stars in the galaxies, I discussed the previous week, in many other areas. But okay, as I mentioned, in the Vlasov-Poisson, you only keep the Gauss law. But if you wish to formulate this as an operator theory problem, as an evolution problem, this is a nice evolution equation, but this is a constraint. But it's a constraint that has to be satisfied at all times. And it's not true that if it is satisfied initially, it will always be satisfied. So it's not so convenient for a Hilbert space formulation. And then what I am going to do is to recuperate the Ampere equation. The Ampere equation is this equation here, right? There is this one because of the how I expand, and I will slightly modify it. I will introduce I star of G is G minus the mean value. So I will subtract the mean value. By doing so, the Vlasov-Poisson system is going to be equivalent to the Vlasov-Ampere system, and it will make the, it's not Hamiltonian, but the operator that appears in the Schrödinger type equation self-adjoint, symmetric and self-adjoint. So then the Vlasov-Ampere system is the following system, right? And I will add that the initial data has mean value is 0, and it satisfies the Gauss law, And actually, if I take the Vlasov-Ampere system, initially I assume that this is true. Initially I assume that this is also true. Then this is equivalent to Vlasov-Poisson. And the constraint is only required to be satisfied initially, and when I write this as a Schrödinger equation, it will correspond that the initial data belongs to the orthogonal complement of a subspace of the kernel of our so-called Hamiltonian. So it's spectral, it's very easy to characterize, like in Maxwell's equation. I will discuss that later, right? So, and furthermore, this linearized system, under this condition, has a conserved energy. And then the conserved energy gives us the scalar product. So, this is the kinetic energy, and this is the energy of electric field. So, Landau damping without magnetic field means that all this energy goes there. And this expresses then the conservation of the energy, and is the basis, the formulation of our magnetized Lasso persistent for the Schrödinger equation in the Hilbert space, where the magnetized Lasso Ampere operator is self-adjoint. Now, notation L2 is just a standard Hilbert space, square integral of functions in 0 to pi, and L2 0 is the subspace of functions with 0 mean value, right? And when L2 of R2 is a standard Hilbert space, or functions square integral. And A is L2 0 to pi times L2 of R2, and the space of so our physical space is A times the L2 0 for the electric field. And then I will denote U, the density distribution, linearized, F, the magnetic field, and this is the scalar product. Now, for solutions to the magnetized Lasso-Ampere system, this scalar product is conserved, and actually it's twice the energy. I take the 1/2 because it plays no role, right? And then this can be written as follows, right? The magnetized Lasso-Ampere system can be written in this form, right? Where H is the magnetized Lasso-Ampere operator. This is H sub 0. This corresponds to, just transport. Transport in the presence of the magnetic field. This is the unperturbed part. And this is the perturbation, which is, those are integral operators, right? Well, this is multiplication by a function. This is the joint, but in the space. There is I star here, and this I star made this object self-adjoint in a proper domain, right? So, and then this is an original formulation that, it's rather new, and it's equivalent to the standard one that is used typically both by mathematicians and physicists. But now this is a nice problem, because now we are in a situation we know very well, right? I am in a Hilbert space, I have a self-adjoint operator, I have a Schrödinger equation. Yes? Sorry? Well, you could take some other. Then what's going to happen is that the interaction will change and so on. Right? The Maxwellian is actually, if you go to the physics paper and also mathematical papers in this area, that's what they use. But you could just take a homogeneous state. If it is not homogeneous, well, then it will be more complicated. But as in the case of galaxies, I could take non-homogeneous as well. But Maxwellian is a very popular situation, right? So then this is the perturb problem, this is the perturbation, which is a nice operator. Now, and the domain of H is domain of H0 times L2. And well, you have to be somehow careful because it's transport. and then the transport will not increase regularity, right? If you have an initial data with the singularity would remain. So it has to define with care, and but we can say that what is required of functions u, that such that this quantity belongs to A. It's a bit more complicated, but you can think in these terms. So then H is self-adjoint, and then what is going to be proven is that H has pure point spectrum. And this is done by explicitly evaluating all the eigenvalues and eigenvectors. What is useful because this allows them for numerical computations and to compare these even with the solution of the nonlinear problem. But there is a nice abstract argument that gives, if not all, at least it gives the fact that it's pure point, but it doesn't give us much information in the where they are, the eigenvalues, and so on, right? This is the abstract operator theoretical argument. And now this explains the Bernstein-Landau paradox, because the general solution now is a linear combination of eigenvalues. Some of them are zero. This gives rise to time-independent solutions, and the others are oscillatory. The eigenvalue zeros and these solutions, well, apparently were not observed before, not in the physics, neither in physics nor mathematically currently. And then there is a change of domain here, actually. Now, when the magnetic field is present, we require that this is true. But when it's not present, it's only this that we require. So as long as omega c is different from 0, this is a nice analytic family of type A of Kato. And then we know that the eigenvalues are analytic and so on. But when omega c is 0, then the domain changes immediately in a broad dramatic wave. And we know very well from perturbation theory that then the spectrum can change dramatically as well. And this is what happens here. So for this, from this point of view, well, there is no mystery here. But of course, once you understand a problem, often it's simpler, right? But you have to understand it first. And actually similar to what happens, it just what happens with harmonic oscillator, right? When omega is different from 0, it's pure point spectrum, there are no eigenvalues, and continuous spectrum when omega is 0. So Bernstein-Landau paradox is a well-known fact in a singular perturbation of self-adjoint operators. But we are also going to obtain some results which are new for this problem as well, right? Now, then the problem is to compute all the eigenvalues and to show that they are a basis. This requires some Weil-type estimate of eigenvalues that I will discuss later. So then I do this by explicit computations, but this is not only useful in the analysis of this paradox, but is the basic of a numerical evaluation of these problems. And it can be used for other purposes because we now know all the eigenvectors, all the eigenvalues this problem has. Some of them are the Bernstein mode that are known in Bernstein, some of them are new. So, and then this is the abstract that if I time, I discuss that. Okay. So, then I will discuss the first method. For all the formulas, which are not so simple, they involve Bessel functions and so on. There is the paper, but let me give you a description of what they are, right? Well, the kernel is infinite dimensional. There are 3 families of solutions. N star are the positive integers, C star the non-zero integer, and they have been computed, and if you are interested, they are in this paper. So there is an infinite dimensional kernel to begin with. But when I solve this, I am not imposing the Gauss law. I have to impose it later on, and I will discuss that. And then, oh, this is here. These eigenvalue zeros allow us to express the Gauss law in a convenient way as an orthogonal relation in H. So H goes is the span of this eigenfunction, not all of them. There were the F as well. And then UF satisfies the Gauss law if and only if UFT, well, this means transpose, is orthogonal to this subspace. So I can express this as an orthogonal relation in Hilbert space. This means, for example, that is time independent. If I evolve along H, satisfy initially, will always be satisfied, right? And there are other problems. For the Maxwell's equation in waveguides, the Gauss law is equivalent to being orthogonal to the full kernel. That's the difference, interesting. It's often the case that it's orthogonality to the full kernel. And this is, I wrote this monograph, well, I could say a few years ago. And there this is discussed for Maxwell's equation in waveguide. At the beginning, I was thinking it will be the same, but it's similar, but you have to take a subset of the kernel. And then the issue of the Gauss law is trivialized. So you just take initial data that are in this AG orthogonal, and you don't need to bother about that anymore. So, and then there are the eigenfunctions with eigenvalue different from 0. And there are several eigenfunctions, this one, and then this CNM. This is an orthogonal basis of the kernel. And these ones have eigenvalues, the mass, well, we took the mass, m times omega c, which is different from 0. And these are infinite dimensional, right? And these also as well. So there are a set of eigenvalues, m omega c, infinite dimensional, which are the same as the eigenvalues of the H sub 0. And then there are these eigenfunctions, which eigenvalues that satisfy this by asymptotics. So they are m omega c times order 1 over n squared times order 1 over m as m, well, this n is fixed here as m goes to infinity. And these quantities appear in the calculation. Now, these ones are the ones that were discovered by Bernstein, and they are known as the Bernstein modes. And then Bernstein observed that all of these are different from 0, and then there's going to be oscillation, right? But there are the others that we found by actually formulating this problem in this way. And then, so what's the general solution? With a complete orthonormal system of eigenvalues, we can compute the general solution to the Blasov-Ampere system. And I present this for the density only. Remember, this is the density. And it has two parts. It has a static part and a dynamic part. The static parts involve these eigenvectors. This is the first component of the eigenvector Fn. And, well, these integrals, right? So there is a static part, and there is the dynamic part. The dynamic part actually corresponds well, if you go to Blasov-Poisson, to what Bernstein found. So, see, this is then the expansion in terms of the Bernstein modes, right? Now, for general initial data, there is also the static part of the charge density fluctuation. And this is interesting because I think you have a plasma. There are so many electrons there. But then you can choose the initial data in such a way, of course, each electron is moving, but on the average, this is static. So if you look the plasma from a macroscopic point of view, it's not moving, right? This is, I think it's interesting. And the existence of this static part seems to be new. It's not reported in the physics literature, but sometimes the physics papers, it's not clear what they are looking for, right? So they don't state it, there's no theorem there. But what is Interesting also in the mathematics literature, well, it was not observed. There is a paper by Bedrosian and Wang. Bedrosian is a very well-known researcher in this area. In their theorem, they claim that the static part of the charge density is not present, so it's identically zero, and that there are only the oscillation Bernstein modes. And they consider the problem in the case of 3 dimension for configuration and velocity. But in Appendix 2 of our paper, we construct explicit static solutions also in their situation. And what happened is that, as done in the physics literature, they use Laplace transform. It's rather intricate, not simple computation, and they just did not observe the pole at zero frequency. So this is a new result. For one thing, we are understanding it as a point operator theory, but there are also new results that we obtain here, right? Now, let's say a computation of eigenvalues. Well, the eigenvalues are the roots of this secular function, and they have this form. This is 0, right? And they are here. I am computing now the lambda nm, the Bernstein modes, the eigenvalues of the Bernstein modes, right? And you see what they are. These are here omega cm, and then they are in between. And actually did not mention, but they are one-dimensional, these modes. The other eigenvalues are infinite dimensionals. These are one-dimensional. Right? And then if I take now the solution, I initialize with an eigenvalue. With this eigenvalue, actually lambda mm is minus lambda m minus n. And these are numerical results. We take nm1, 2, omega c 0.5, and the final time in the computation is actually p over 2 lambda 1, 2. This means that UTF is IU initial. Right? So then in this case, we know that we just exchange real and imaginary part, and the imaginary part, there is a change in sign, right? So the solution at TF corresponds to the initial condition where the real up to a sign and the imaginary part has been exchanged, right? And well, there are so many calculations here that we say, well, let's see if actually there is some mistake somewhere, because here we know exactly what it has to be, right? And then we present the imaginary part, the real and imaginary part of the first component. The first component is the distribution function. The second, the electric field. In the V1, V2 plane for x equals 0. And then you see, I think you managed to see it because it's quite large. This is the real part at t equals 0. And then the theoretical at the final time, and the numerical at the final time. Theoretical meaning using our formulas, and numerical, well, we develop a numerical method to evaluate this, right? If you are interested, it's not so trivial, because, or later on, because of the 3 dimensions and so on, the idea of the method is explained in the paper. So, and you see that this behaves actually as it should, right? If you compare, you see that there is a exchange of real and imaginary and the change of signs here. So this was somehow to verify that at least it was not an obvious mistake. And this is the modulus of the first component in V1, V2 plane for x equals 0 and the real and imaginary parts. And then you see that the modulus won't change. And here you see the curves and the other curves that they behave, they really exchange real to imaginary with -1 and so on. So this calculation is, was somehow to verify the method. So this is what we did. And then we go to the nonlinear system. all this was for the nonlinear system. So what we wish to do is now to compare and also to see to which extent the linearized equation follows the real nonlinear problem. This is what in the following picture we show how the solution to the nonlinear magnetized Blasov Poisson system behaves when initialized with an eigenfunction of our problem. Now, for the nonlinear magnetized equation, well, I take real parts. Everything was complex because we're working with Hilbert space method, so it's better to be unitary evolutions and so on. But then we take real part. So this is, we initialize as follows. Remember, this is how we decompose, and this is now the real part of the eigenvector for the corresponding eigenvalue. And this is, there is an epsilon here, right? This is the first component of the eigenfunction u initially, and Fn is the second component. Epsilon is a scalar, which controls the amplitude. Epsilon is 0.1, and then nn12, omega c 0.5, and again we do in such a way that we exchange real and imaginary. And this is what we compare the theoretical perturbation, which is given by that, right? So this is just the solution of the eigenvalue problem with the numerical perturbation. So we have to, U is the one that corresponds to this one when we do the change, and F is electric field divided by epsilon. And we plot U in the V1, V2 plane for x equals 0 and electric field F. And this is what it is. Now you see what is the theoretical at t equals 0. So this is t equals 0, theoretical and numerical. Numerical means solution of the nonlinear problem. Right. And here we compare. You see that it goes very well, very well, very well, but eventually it's not so well, right? No, and they are also not so well, and they are not so well. But it's still reasonable, this comparison. And then the Bernstein-Landau paradox. We illustrate now the Bernstein-Landau paradox numerically, and we compare it with Landau damping, in the case omega c equals 0. So what do we do? Well, initially we take this function, right? This is just what we take. This is epsilon, this is k here. And we take k 0.4 in this simulation. The position interval is divided by k because, well, we wish to be periodic, and we do that because there is an explicit solution that is well known, that is in, that's periodic with this period, right? Now there is an approximate solution to the nonlinear, the real nonlinear system without a magnetic field. This is Sonnenrucker. This is lecture notes from a class that I give in France. He's Strasbourg, actually. He's quite active in this area. And this is this solution. This form is a good approximation for large time because there are a number of terms that you just take away. But then this solution is often used in this area to test numerical methods. So this is the one we use to compare, right? And then this is, okay, this is Landau damping, right? Now, numerical is the result of our numerical calculations, and E is E theoretical. It goes very well, more or less well, but eventually begins to be different. So, and then this is the Bernstein-Landau paradox. Now we take the same situation with omega c 0.1. This is numerical and theoretical. Theoretical, again, this is to compare with Landau damping. This is the explicit formula that I gave you earlier. And you see now that this is a kind of a recurrence relation. And actually, it's on the paper. I will not have time to discuss, but using our expansion, we actually prove that, or justify, this recurrence that appears in the Bernstein-Landau paradox. So it's not just oscillating, it's doing like something like that, and then something like that. And this is a consequence when you expand, there are several modes, and then they add in a way or in a different way. So this is this question. And let me see, how much time do I have? 5 minutes. So, okay, now, if I only wish to know that the spectrum is pure point, there is a very easy answer using the invariance of essential spectrum, which is the following. Well, I use Fourier series, right? And then this corresponds to, well, a constant term, and there is no electric field because it's means 0. And then these are all the others. And then I can write a general function in this space in this form, where for n equals 0, alpha n is 0, and this one is an orthonormal basis in A made of eigenfunction of the Blasov operator. So I just take the Blasov operator, not the coupling given by the perturbation, right? Well, and by Fourier series, actually, to prove that the whole problem is pure point, is enough to prove that each one of these has pure point, where H0n is multiplication by the eigenvalue times this, where this is 0, which this domain, and Vn, and the spectrum of H0n is pure point, and it consists of infinite dimensional eigenvalues. So the m omega c, those are infinite dimensional. This is crucial here, right? Yeah, lambda 0m, which was m omega c, right? Well, the discrete spectrum consists of isolated values of finite multiplicity, and the essential spectrum is a complement. And then this is now the perturbation, right? But the perturbation has rank 2. Then it leaves the essential spectrum invariant. And since the essential spectrum was m omega c, we know that to m omega c, we add eigenvalues of finite multiplicity that at most would accumulate at omega c. And this is enough. Just to know is discrete is very simple, right? But of course, it doesn't tell you, we know much more. We know that you only add one-dimensional eigenvalues, and we have a Weil formula for them, and we have all the eigenvectors, right? So this is an example of the operator theory. Often give you part of the problem, but if you have an explicit solution, of course, you know much more, right? So this is what I explain here, right? So we know that it's pure point, and this proves that the spectrum is, but it's almost immediate between the formalism of Blasov-Ampère. If you would like to do using Blasson-Poisson, well, it's not so clear, right? So this is what it is, and then, well, I thank you for your attention, and I think I am just in time, if not about.
Yeah, thank you very much. So we opened the discussion. Are there questions? So let me ask a question. Did you, for the nonlinear equation that you studied, can you perform some kind of stability analysis around the linear equation?
For the nonlinear equation, we only did some numerical calculations. And in the mathematics literature, there is Landau-Dam. Well, okay, in the case with magnetic field, in the plasma physics case, I haven't seen any result. Actually, there are very few, the only mathematical papers I know when there is magnetic field is our own and the one on Bedrosian and one that I mentioned. So this field is wide open. So there are there are many physics papers, right? But mathematical papers, yes?
Irren.
Thank you for a good talk.
Well, thank you.
I was wondering, I'm new to the field, but so when you have this constant magnetic field, somehow it feels that is continuously putting energy into the system. Is that a natural assumption to have this constant magnetic field, or should that be dynamical, just like the electric field is?
Well, okay, you have the constant magnetic field, if you think in a tokamak, is what you wish to have, right? But then the energy of the system, electric field electrons, is conserved. So this actually is a conserved quantity.
Yeah.
So what the magnetic field does is, well, modify the force and modify the dynamics. But it's the real issue is that there is also a small induced magnetic field. But if you have a huge, in the Lorentz force, there is a big external and the small ones, and you take it away. So this is a natural model in the context of a tokamak, for example, or in other situations as well.
Thank you.
Welcome.
Okay. I don't see any further questions, so let's thank Ricardo again for the nice presentation.
Thank you for the invitation.
And we'll continue in about